All right, everyone, get ready, because today we're going deep, diving into the world of linked structures in C.
Yeah, we're going way beyond just what they are. We're getting into why they matter so much.
Exactly. So think about it. Data structures, they don't always have to be these rigid containers.
Nope, not at all.
We can make them flexible, like chains that grow and shrink as we need them. And that's the beauty of linked structures. We're going to break down how they work, why they're so powerful.
And most importantly, how to use them effectively in your C programs.
Absolutely. So before we get into the nitty-gritty, let's quickly recap something crucial in C modules.
Right, the building blocks of our program.
Exactly. Think of them like Lego bricks. We've got our header files, those .h files, which are like our blueprints, declaring what's inside each block.
And then there's our source files, the .c files, where the actual building happens, all the instructions and details.
Spot on. And we need to be comfy with these modules, especially with linked lists, because they help organize our code and keep everything tidy.
They really make our lives easier in the long run.
Now, speaking of linked lists, can you give us a crash course on what they are and what makes them so special?
Absolutely. Imagine, instead of storing your data in a fixed size box like an array, you thread it together like beads on a necklace.
Okay, I like where this is going.
Each bead is a node, and each node holds not just a piece of data, but also a pointer. Think of this pointer as a little arrow directing you to the next node in the sequence.
So each node is like a link in this chain, and the chain can grow or shrink as we need it to. What's the advantage of that?
It's all about flexibility. With linked lists, we can easily insert or delete elements without this big reshuffling act you'd have with an array. Imagine trying to add something at the beginning of a packed array. You'd have to move everything over to make room.
Yeah, that would be a pain.
Especially with large data sets, it's incredibly inefficient. Linked lists sidestep that whole issue. You just change a couple of pointers and boom, you've slipped your new element right in.
That's clever.
Yeah.
So much smoother than shifting everything around.
Now, let's make this a bit more concrete. Take a look at this slide from the lecture. It shows a simple linked list, elements 4, 8, 2, and 6. Each number represents a node, and see those arrows. Those are our pointers connecting them all up.
Okay, got it. But the last node, it has a pointer pointing to nothing.
Ah, that nothing is actually an NLL pointer, and it's way more important than it looks. It's like a stop sign for our code, signaling, hey, you've reached the end of the line.
So to find a specific element, we'd start at the beginning node and just follow those pointer arrows until we either hit the jackpot or we bump into that NLL sign at the end.
You got it. And that little journey through the list is what we call traversal.
Traversal, it does sound kind of venturous. But wouldn't it be faster to just jump directly to an element in an array using its index?
You're right. Arrays are definitely faster when you need direct access to a specific element, but linked lists, they shine when it comes to inserting and deleting elements, especially if you're doing it frequently. They're the kings and queens of dynamic data manipulation.
Makes sense. We're trading a bit of speed for incredible flexibility.
Exactly.
So we've got this abstract idea of nodes connected by pointers, but how do we actually build this in C? What's the code look like?
That's where our trusty friend, the struct, comes in. We're going to define a struct called node to represent each of these elements in our linked list. Think of it as a custom data structure that can hold different types of information together, all bundled up nicely.
Structs, like those handy containers for our code.
Exactly. And in our node struct, we'll have two main components. Element, which stores the actual data, like those numbers in our example, and pnext, which is the pointer that holds the memory address of the next node in line.
Okay, so if our linked list was a line of people, element would be their name, and pnext would be like them holding hands with the person behind them.
I love that analogy. And if you look at this next slide, it shows how this node struct, with its element and pnext, directly translates into that visual representation of the linked list we were just looking at.
Ah, so this is how we bridge the gap from those abstract notes and pointers to a visual structure we can actually code.
Precisely. Now let's think about a unique situation, an empty linked list.
An empty list, so like a chain with no links.
In a way, yeah. You see, in C, we represent an empty linked list with a NUL pointer.
Interesting. It's not just an empty space. It's like we're specifically saying, hey, there's nothing here on purpose.
You've got it.
Yeah.
And that distinction is super important as we start doing more complex things with our linked lists.
This is really starting to click now. We've got the basic idea of linked lists, how they work, and how to actually represent them in C. Now, I'm really curious to see how we actually make them dance in our code. All right, so we've got our nodes all prepped. We see how they link up. But where's the code that actually makes this linked list thing go?
That's where our header file struts in. LinkedStructure.h. Remember, it's like that blueprint we were talking about.
Right, the instruction manual before we start building. But gotta be honest, header files always feel a bit like a secret code to me. What's the deal with all the stuff in there?
They're not as scary as they seem once you get how they're organized. Let's take include guards, for instance, those lines that start with hashtag. They might seem a bit mysterious, but they're actually pretty crucial. They make sure we don't accidentally include the same header file multiple times, which can really mess things up.
So like making sure we don't order two sets of instructions for the same Lego set.
Exactly. And then we've got our standard library inclusions. That's where we bring in those pre-made tools, functions, the things that are used all the time in C. It's like getting all your tools together before you start a project.
Makes sense. What about the actual code for like creating and changing our linked lists? Where's that lie?
That comes next. In the header file, we declare the functions, what our linked list can actually do. We're basically saying, hey, compiler, these functions are here. This is what they should do, but we don't actually write all the details out yet. That's what the source file linkstructure.c is for.
So it's like we're setting the menu, showing all the tasty options, but the actual cooking happens in the kitchen, which is our source file.
Exactly. But before we jump into the source file itself, there's one thing in these function declarations I want to point out. Notice how some of them need a pointer to a pointer of the first node. Seems a tad complicated at first, but there's a good reason for it.
A pointer to a pointer. Now you're just messing with me.
Not at all. Think of it this way. When we change the link list itself, like adding or taking away elements right at the start, the starting point of that whole list can actually change.
Right, because we might have a new first node now.
Bingo. By passing a pointer to a pointer, we're basically giving our function the power to change the address that the original pointer is pointing to. It lets us modify the very beginning of the list if we need to. In the code, you'll notice the function argument is struct nodehead. That double asterisk there is the giveaway we're dealing with, a pointer to a pointer.
So it's like giving the function the power to rearrange, not just the links in the chain, but also where that first link is hooked up on the wall.
Perfect way to put it. Ready to dig into the source file? LinkStructure.c where the real action is.
Let's do it. Bring those functions to life.
Okay, let's break it down. Just like any C file, we start by including those necessary libraries and our header file linkstructure.h.
Gathering our tools and instructions, just like you said.
Exactly. Now check out the first couple of functions, node new and node free. These are our helpers, all about managing the life cycle of those nodes.
Lifecycle management sounds kind of deep.
Basically, node new is in charge of making new nodes. It gets some memory for the node, sets up its members, that element, and the pnext pointer. It's like our node factory. Node free, on the other hand, does the opposite. It cleans up, frees up that memory a node was using when we don't need it anymore. Super important to avoid those memory leaks.
So node new is the construction crew building our nodes, and node free is the demolition crew, making sure we don't have a bunch of unused nodes just lying around taking up space.
Perfect analogy. Now let's move on to link structure new. As you can guess, this one's all about creating a brand new, totally empty linked list. Remember how we talked about representing an empty list?
With a NOL pointer, it's like we're saying this list starts nowhere, at least for now.
You got it. That's exactly what this function does. Returns a NOL pointer, showing that initial empty state. Simple but effective, right?
Absolutely. Yeah. Okay, so we've got the foundation laid. We can even make an empty list. But how do we start adding stuff to it? How do we actually put something onto this linked list?
Great question. There are actually a couple of ways we can do this, each with its own logic. We can start by looking at prepending adding an element at the very beginning of the linked list.
Sounds good. Let's hear it. So if I'm picturing this right, it's like we're adding someone to the front of a line. How do we actually do that in our code?
It's honestly simpler than you might think. First things first, we use our node new function, the one we talked about, to create a brand new node. We give it the element we want to add. Then we tweak the pnext pointer of this new node to point to the current first node. Easy peasy.
So our new node, it's like it cuts to the front of the line, right? And the node that was first before, it's second now. But its pnext is still pointing to the right place further down the line.
Exactly. And here's a little detail, but it's important. If the list was empty to begin with, meaning the head was just a NUL pointer, our new node, well, it becomes the first and only node. No line to cut in front of. In that case, we set its P next to NULL, showing that it's the end of the line for now.
Makes sense. Now, what about adding to the end of the list, appending it? That feels like it might be trickier.
You're right, appending does take a bit more work. We still make our new node, of course, but now we got to do some searching. We need to traverse, remember that word, full, the entire list until we find that last node. And how do we know it's the last node? Its pNext will be that NUL pointer.
It's like walking down that line of people until we find the one who's not holding anyone else's hand.
Precisely. We find that last node and we change its pNext, which was pointing to NELL, to point to our shiny new node. Bam, we've appended it. And just like before, if the list was empty, our new node is it, the first and only one.
Okay, I'm with you. We've done adding at the beginning, adding at the end. But what if I want to get fancy? What if I want to insert a node right smack dab in a specific position?
Now you're talking. That's where things get interesting. We've got a function called link structure insert for that. And yeah, it involves getting a little clever with our pointers, but
Yeah.
no worries, we'll take it slow.
Whenever you say pointer manipulation, I always imagine those crazy chain link sculptures. One wrong move and the whole thing could unravel.
Haha, I get it. Don't worry, we're not going to unravel anything today. Okay, let's say we want to add a node at position 3. We start traversing the list, like before, but this time we bring 2 pointers to the party. P previous and P current.
So it's like two fingers moving down the line of people, one right behind the other.
Exactly. As we move along, P current points to the node we're looking at right now, and P previous is trailing right behind. When P current gets to position 3, P previous will be sitting pretty at position 2, ready to make some magic.
I think I see where this is going. We're going to use those 2 pointers to sandwich our new node right into that spot.
Nailed it. We set the pNext of our new node to point to what P current is pointing at, and then we tell P previous, hey, your new pNext is this new node. It's like we're carefully opening up the chain, slipping in our new link, and welding it all back together nice and neat.
That is so clever. Now, we've done adding elements every which way, but what about removing them? That's going to be important too, right? The flip side of building these dynamic structures.
Absolutely. And for that, we have link structure delete. Just like with inserting, our good friends P previous and P orient are back to help us out. We're going to surgically remove a node, nice and clean, without messing with the rest of the list.
So, same idea as before. If we want to delete the node at position 3, we move our pointers until P current is there, with P previous right behind it at position 2.
Exactly. To get rid of that node, all we got to do is tell P previous, hey, skip over that node in front of you. Your new pNext is the one after that. It's like snipping out a section of the chain and then welding those 2 loose ends directly together. Seamless.
And then we can use our trusty node free to clean up that deleted node's memory. Right. Make sure we're not leaving any digital clutter. This is really amazing when you think about it. We're not just storing data, we're messing with it on the fly. Adding, removing, finding what we need, all with this chain of nodes. So cool.
That's the beauty of linked lists, and honestly, we've just scratched the surface. They're everywhere in programming, managing playlists in music apps, building those complex algorithms in data science, you name it. Linked lists are fundamental, a real cornerstone in computer science.
Wow, I had no idea. This deep dive has really opened my eyes.
And to keep those brain gears turning, are you up for a final challenge?
Hit me with it. I'm feeling way more confident about tackling some linked list puzzles now.
All right, here we go. Let's say we want to keep our linked list sorted. Not just any old chain, but one where the elements are always in order. Your challenge, should you choose to accept it, is to create a function called sorted insert. This function will take a new element and find the perfect spot for it in the list, making sure we maintain that sorted order.
Ooh, now that's a good one. Any hints? You know I love a good hint.
Remember our pointer pals, P underscore previous and P concurrent. They're going to be super helpful here. If you think about it, you need to go through the list, comparing your new element to the one in each node. Figure out where it fits in that sorted order.
So it's like we're finding the right spot in a line of people who are already lined up by height or something.
Exactly. And don't forget about all the possibilities. What if the new element is smaller than everything else in the list? What if it's bigger? Where does it belong? It's all about thinking through the logic.
I'm going to need my thinking cap for this one. Yep. But hey, challenge accepted. I'm up for it.
I knew you were. That's the spirit. It's a really satisfying feeling when you crack the code and get that sorted insert working. Trust me.
I bet. So to all our listeners out there, if you're feeling adventurous and you want to really test out your linked list knowledge, give that sorted insert function a try. You won't regret it.
And remember, that's what's so great about programming. There's always more to discover and explore. Linked lists, they're just the beginning. There's a whole universe of data structures and algorithms out there.
So true. Well, we've come a long way. We started with nodes and pointers, those basic building blocks, and now we're building these complex operations in C, all thanks to linked lists. You're well on your way to not just acing those exams, but truly becoming a linked list master.
Couldn't have said it better myself. And who knows what amazing things you'll create with this knowledge. The possibilities are endless.
That's what I love to hear. Thanks for joining us on this deep dive into linked lists, everyone. Keep those coding brains fired up, and we'll catch you in the next episode.